And one side of this interval I'm putting for AI, I put A1, I put A1 semicircles. For A2, I put A2 semicircles with the all centered at the center of the interval, and A2 and AN. So this way, given A1 to AN, with sum is equal to N, I get a shape of, so it's now I had my half circles here, and I added this half circles which depended on A1 to AN, but that basically A1 to AN determines a shape like this. And the question is, what is the probability? So you can start and go around either, I mean, at some point you will come back to the same place, but it could cover the whole thing, or this could be just a connected cycle. Of getting a connected cycle. Or two of them, or as n goes to infinity. Sorry, n it goes to infinity, and sigma I is equal to n is somehow a random point in the random point where AIs are integers. So, okay, so this is a little, yeah, so you can certainly generalize this kind of questions very easily into, we play with this a little bit, you'll see that you can very easily make this into a question about, there's nothing about the semicircles or the way we define this. We can start from a graph, and maybe I can, I mean, you can see even the interval in this. You can start from a graph, and you can have n incoming edges and n outgoing edges. And then you have this here, you can have a permutation. To join the incoming and outgoing edges. And each, say, if you want to make the problem easier, each incoming edge will go to, maybe I have 1, 2, 3, 4. Maybe 1 goes to 4, 2 goes to 3. And of course, I can't draw it on the plane, but it's okay. I look at it as a graph. 3 goes to 2, and 1 goes to 4. So, okay, it's just a graph. And then if you assign A1, A2, A3, A4, where the sum of AI is equal to large capital N, you can basically do the same thing that we were doing here, meaning that I can just put something very similar to that without using circles. I can just use these integer points, AIs, to draw parallel lines. So if I have 1, and therefore I'm looking at the number A1, I'm putting A1 lines parallel to the first one, and then I'm putting A2 lines, not even parallel, but A3, A4 here, and here I'm putting again A1, if A2, whatever these numbers are. And I'm just connecting, and here I'm just using, I have now, because the sum is capital N, I have capital N strands here and capital N strands here, which are joined 2 different ways. So one way is just this here, it's just without any self-intersections. And the other way is through the lines of the graph. So A1 to AN will determine a loop. And the question is, when is this loop connected? Or what is the probability of, to be more precise, probability of getting a connected loop as basically n goes to infinity. So maybe this, you choose from A1 to AN integers uniformly by restricting that the sum is less than or equal to n. That's the probability of getting it. It's sort of hard to get something connected, and if you want to see what it means, you can put some conditions on these integers to see when it's connected and it's not, and to get a sense of this, you can do it with the simplest possible graph with two. This goes here, and this goes here, and if I put A1, A2, and A1, A2 here, sorry, and A1, A2 here, sorry. What I'm getting, so what I'm getting here is that, so the loop is connected if and only if A1 and A2 are co-prime. So you get asymptotically, as n goes to infinity, you get something about the probability of getting a connected arc, which is non-zero, which is the probability is 6 over pi squared, which you can calculate using elementary number theory. But as you have more and more intervals and your graph is more probably complicated, then you can't use anything. You can't say if this is connected or it has two connected components, if and only if you can't easily write it in terms of some conditions in terms of AIs. And yeah, but as you can see, this is, of course, secretly, there's a surface behind this question, and the surface is the surface that you get by thickening the graph, which is we start with, it's a ribbon graph, and gluing basically disks to get a compact surface. So for example, if I do this 1, 2, 3, 4, 1, 2, 3, 4, and this kind of thing it's related to the interval exchange math. Is something that people study a lot and they have nice properties. But if you do it, for example, and if you thicken the graph, this 1, 2, 3, 4 that I have there, and basically glue back a disk to make it a compact surface, you get a surface of genus 2. So for this permutation that I have, or as I'm sure most of you have seen, if you do this kind of graph and you thicken it, you get a surface of genus 1. So these are questions related to some topological properties of things on surfaces. And so here's so this is the third question is basically what a generalization of this, that you can start from a surface of genus G, and so you're looking at different maybe patterns on SG, and a pattern, I mean, it could be maybe so that's up to now. So this SG is a subset of genus G, and here I'm only interested in the topology of it. There's no geometry on it, and it could be a union of homotopic classes of closed curves. So, for example, you can have this guy, this guy, this guy. I don't know, this guy, and maybe some self-intersection in the between. So this would be your gamma, and then you want to see basically, so whenever you can draw one picture like this, and even if these gamma i's are up to homotopy, you have a very natural action of a very important group on the set of patterns of this type on the surface, and the action is by the mapping class group of G, which is the group of, say, diffeomorphisms or homeomorphisms here, orientation, preserving, or homeo up to isotopy acts on the set of patterns of this type. So all I'm saying is that if you have a very complicated homeomorphism,